Okay, welcome back everyone. I hope you're ready for Martin Loschwitz topic about an introduction to software-defined networking. Enjoy.
Thank you. So does the microphone work? Can the people in the last row understand me? That sounds great. Welcome everybody to this presentation. Before I get into the subject of SDN, I will actually introduce myself. My name is Martin Loschwitz. I work here in Berlin, as you can see on the picture. I work as the team lead for the OpenStack team at Sys11. Sys11 is a company doing web hosting, and we have invested roughly 2 years of work into evaluating OpenStack and bringing OpenStack into a state in which it actually does what we expect it to do. And one of the things that we have evaluated a lot during this time was software-defined networking, along with multiple solutions and implementations. And today, that is why I stand here in front of you and do a presentation on software-defined networking. So, what is software-defined networking? Software-defined networking really is network virtualization. Thanks. Sorry, any questions? I was trying to be polite for those people needing to leave a bit earlier. Of course, the presentation is going to carry on with a more detailed insight into software-defined networking. And before we understand what SDN actually is, we need to understand how IT has changed over the last few years, because that is fundamental to the understanding of software-defined networking. So, years ago, individual servers had individual tasks. There was a server, or there were many servers in one data center, and then there was a task an individual server was doing. For instance, monitoring could be such a task. So there was one server, and there was a monitoring system running on top of that server, and there was no other task this server was acting for. And in fact, over the last few years, the capacity of servers has increased continuously. So by now, you can actually buy not only servers, but you can buy big servers. Lots of CPU, lots of RAM, and it's almost impossible to use this with a single application, unless you're using Java, of course, but we will not get into that today. So the interesting question is, how can I turn all the capacity in my rack into actual food in my fridge? Because that is what it's all about, right? I'm buying hardware, and I want to use it to the best to make money and to make as much money as I can with the hardware that I have. And this is where virtualization comes in. Virtualization really follows a very simple idea. The idea behind virtualization is to run multiple workloads at the same time on the same machine. Of course, every workload needs to be strictly isolated from the other workloads that I have on the machine. I still have one big server, but I do not have one task for a machine anymore. Instead, I have multiple workloads. So I can have a monitoring system in a virtual machine. I can have a database. I can have a WordPress installation on a web server. I can have a metering system. All these applications are running separated from each other inside virtual machines on the same server at the same time. And I've been using the word virtualization a lot in the last few minutes. The interesting thing to understand, and the important thing to understand in this case, is that virtualization, in the sense that I have used the word in the last minutes, really refers to the virtualization of computing power. So we are not talking so much about virtualization per se, but really we are talking about one individual factor of virtualization, and that is virtualizing computing power. Virtualizing computing power by now is a very well-established technology. We have KVM, we have Xen, we have VMware, we have Hyper-V. For every major operating system, there is at least one big solution for computing virtualization available. And for most operating systems, there are multiple solutions available for virtualization. So in fact, when it comes to computing virtualization, everything is super awesome, and we couldn't be happier with the situation that it currently is. And now the interesting question is, how does virtualizing network work, or how has it worked in the last years? How have we actually done that? And the interesting answer to that question is, actually we haven't. Networking virtualization has not really happened. What we have done is, we have done a concept in which we treated networking for virtual machines exactly like we would have done networking for actual physical machines. And a great example for that is a setup that I have personally seen many times in the wild. I have tab interfaces. And I connect my virtual machines with their top interfaces to a bridge, and I connect a VLAN tagged device on the other side of that bridge, and then I call that virtual networking. It's not. It's exactly what I would do on actual iron, on actual bare metal. And that is not virtualization. That really is just applying the concepts that we have used up to this point on the actual virtual machine that I have. Every person involved in software-defined networking at this point would, and that would be the nicest reaction you could get from that person, just ask you if you are trying to kid them, because that is not virtualization. That is, in fact, only applying old principles to a new scenario. And surprisingly, this worked well for quite a while. We have done this for years. We have basically set up virtual machines like this for a number of years. It involves a lot of manual configuration. So whenever somebody needs a virtual machine, somebody needs to configure a proper network device on that machine, needs to ensure that bonding is available on that machine, and there is a properly configured switch port to which that virtual machine can connect to. And all this requires manual intervention, and it requires a lot of intervention. And now the interesting question is, why is that not good enough anymore? Why can we not continue to do what we have done in the last years, and what obviously has worked out rather well? So, who of you is in the cloud? This is impossible. Everybody is in the cloud by now, right? The cloud is everywhere. So again, who's in the cloud? Who's not in the cloud? Who doesn't want to be in the cloud? Okay. Anyway, the cloud in this case, in this context, is a very important thing to understand, because the cloud is the one reason that enables the requirements for new ways of virtualization on the networking level. In fact, by now, as I have already mentioned, the cloud is everywhere, so everything is the cloud and everybody is in the cloud. If you buy a local storage system by QNAP and install it behind your telephone line, you are in the cloud, according to QNAP. I don't know what these guys... I'm not allowed to say that now. Anyway, so I don't know what exactly the marketing definition of cloud is, but in fact, there is a very clear definition of the cloud per se. And the cloud, in fact, is not so much something completely new. It more is logical evolution of virtualization and actually of computing virtualization. Because what has the cloud really done? The cloud adds two features to computing virtualization, namely the first important thing, automation. So I will no longer have to manually start a virtual machine. I can actually just create a template, and I can start as many instances of one particular virtual machine as I think I need. And I can do that again and again. And I can just do it as many times as I need to. And in the end, I will have a number of setups, all centrally managed, all set up completely automatically, and everything is going to be fine. And the second important factor is on-demand capabilities. So iCloud actually allows me to just log in, create an account, add my credit card data, and I can start virtual machines. And this obviously creates a problem, because by now the expectation is that I can just do this at any point in time. I need to be able to log into the web interface and do that, and it's impossible for me to wait for somebody to create, my account, to start virtual machines for me, or to ensure that these virtual machines' network configuration is proper for the host that the VM is running on. And this is where we have an obvious clash between conventional networking and cloud computing. And cloud computing is the one reason that we need to look into new ways of virtualizing networks in our setups. Conventional networking makes three basic assumptions. Number one is the network is managed centrally and relies on hardware functions such as VLAN. Whenever you take a look at conventional setups, you will likely find switches actually doing management capabilities, and the one that is used most of the time are VLANs. So I have a logical separation of individual customers on the same switch. I have actually something on my switch that ensures that customer A cannot see the packets of customer B and the other way around. The second assumption is machines belong to specific customers. So I install a computer, I install a server, and that server is going to belong to this particular customer. Nobody else, no other customer will be running stuff on that machine. And nobody will be ever able to use it except for the one customer that I bought this machine for and that I built this machine to. And the third assumption is there's little to no requirement for scale out. So a customer now creates an order and he needs a few virtual machines or a server, and we create the setup for the customer, and then everything is going to be fine for a number of months before the customer gets back to me and tells me, okay, I need another virtual machine. And as soon as the customer creates or needs another virtual machine as a provider we just created, this is a very manual process. Whenever we need to create a virtual machine, we need to create the VM per se, we need to create the storage for it, we need to create the port configuration, everything I've already mentioned. Obviously, this doesn't scale and this doesn't work, and this is exactly where cloud computing comes in to help. In clouds, first of all, the networking is managed by customers and cannot rely on hardware functionality. So I cannot assume that I can reconfigure my switch just because a new customer has registered himself and has created an account and now wants to use a virtual machine inside the setup. Servers host VMs of multiple different customers. In fact, I cannot dedicate a server to a particular customer inside the cloud because all servers need to be exactly the same. They need to be configured the same, they need to have similar capabilities, and I must be able to start any customer's virtual machine on any server because everything else does not scale, and anything that doesn't scale inside cloud computing environments is not going to work very well. Virtual machines come and go, static configuration doesn't work. I cannot assume that a customer does not want a new machine just because he created 5 of them yesterday. At any point in time inside clouds, I need to expect my customer to come and say, okay, I need another 200 virtual instances, and I need to create them myself because I have the configuration for that in place, I have all my automation frameworks properly configured, and I can just create those 200 things. And if my customer comes to me and tells me I need 200 VMs, I just cannot tell one of my administrators, okay, please create 200 bonded ports on individual servers because that is what the requirement currently is. And that is exactly why conventional networking and all this manual stuff, creating ports, configuring switches, does not work in cloud computing environments. And this is where the requirement for software-defined networking actually comes from. The interesting question is, can we fix it? So what can we do to work around the shortcomings that I have just mentioned? Number one, network virtualization needs to fix these 3 issues of conventional network. It needs to make networking functionality independent of the hardware in use. I cannot ensure that configuring a switch is possible. So I cannot rely on any functionality that my switch is only going to provide if I configure it accordingly. In fact, I need to turn my switch into something very dumb. My cloud computing and virtualization environment needs to allow me to configure the whole network from within the actual platform because my customers need to maintain their own network configuration and their own network topology. I need to enable them to do that. I need to offer them functionality to just create their own virtual networks without any manual intervention from an administrator. And the cloud also needs to make it easier for cloud customers to set up their own networking topology. In fact, inside clouds, as a provider, I do not want to have anything to do with my customers doing their networking configuration. I want them to do this all on their own, and of course they are free to contact me if they run into a technical issue, but that is something that is up to them. I do not want to know anything about my customers' networks, because that is something that they need to do, and only they have the actual knowledge to run whatever setup they may require. This is a screenshot taken from OpenStack Horizon. So this is the virtual software-defined networking module that you can find in OpenStack. Here you can see that customers have created virtual networks for themselves. We have a number of external networks, we have internal networks, and customers are free to create as many virtual networks as they think they require inside this platform. So in fact, whatever customers do, they must be able to do it on their own, and they may not require any intervention from me as the provider. How can we do that? What is the technical means? What are the technical means to actually implement this type of networking inside our installation? The most important thing you need to understand about software-defined networking is that software-defined networking really is about decoupling. Decoupling is a word that you will hear a lot in the cloud context, and it hardly applies as well to anything as it does to software-defined networking. Decoupling means separating one thing from another. What are we actually decoupling? What are we dividing from each other? we are dividing networking hardware and networking functionality. This is the part where I actually earlier mentioned that you cannot reconfigure your switch. So if we have a switch and we now rely on the switch's functionality, and we need to find a way to no longer do that, we need to implement the functionality by the switch somewhere else, and we need to implement it in a way that allows us to influence it from the running setup. Here's what you typically have inside a data center. You have a host. In this case, that is the host running our virtual machine, so this is the hypervisor. And there's the switch. The switch typically has two components, the control plane and the data plane. The data plane is the boring part of the switch, because all the data plane really does is sending packets from one port to another. So as soon as you just use a switch to send packets from one server or from one virtual machine through a server to another VM on another server, all you really use is the data plane. The VLAN capabilities and all other management functionalities typically provided by switches actually reside in the control plane. And what we need to do is we need to decouple the control plane from the data plane. So we need to make sure that these two components are separated from each other. And we need to move the control plane onto the host. Why do we need to move it onto the host? Because that's the place that we can influence from our cloud setup. We have components of the cloud running on our host, and actually, we can influence the configuration of the host, and hence we can influence the configuration of the control plane on the host if we actually virtualize our control plane. And that's really what software-defined networking actually tries to achieve. It really tries to decouple the data plane and the control plane on switches. Of course, this effectively renders switches into dumb packet forwarding devices. I have already mentioned that. The important thing to understand is any major management functionality your switch is able to provide in a cloud computing setup is probably going to be useless. And I've seen customers running this with switches that didn't have any management capabilities at all. This is something that actually can turn into a problem, because typically those switches that do not have any management capabilities also provide only very few resources, so they are not very capable of doing anything. But in fact, you wouldn't need most of the management functionality on your switch. You should be able to run a software-defined networking without any particular switch configuration at all. The network that your machines, your actual bare metal servers belong to, in fact, should be a completely flat network that all servers are equal parts of. Step number 2 on our way to proper network virtualization. Make your virtualization configure the network for you. So whatever sort of virtualization you use, and even if it's not the virtualization solution itself, but more precisely the software that is running your cloud computing environment, such as OpenStack, you need to make that part influence your configuration. So in fact, you need to use OpenStack or CloudStack or VMware or whatever your solution for virtualization is, and you need to make that component configure the control plane on your individual hosts. And that's the way to go. In fact, if you manage to do that, you can offer your customers a completely virtualized network environment, and they will be able to perform any configuration they consider necessary inside the setup. Let's dive a bit deeper into this. Let's take a look at the actual technical basics. What are the technologies in use? It's easy to say that we need to virtualize the control plane of switches, but how does that work on the actual technical level? Almost all SDN approaches split the network into 2 logical layers. These are also 2 words that you will hear a lot inside the SDN context. The first name actually is the overlay, and the second is the underlay. The underlay is what is happening on the hardware side of things. So this is where our machines are talking to each other. This is the flat network on my switch. This is the network, this is the physical link that my machines use to communicate with each other. Then I have my host. In this picture, the complete orange area is one host. I have a hypervisor. In our case, it could be KVM. It could be XEN. It doesn't really make a big difference. And then I have my virtual switch. And as we already understood, the virtual switch in this case is our control plane. The big difference is that on a switch, I only have one control plane. And on my other SDN-based setups, I do have multiple control planes, and I need the control planes on my individual hosts to communicate with each other in some way. In fact, how do we do that? How do we implement the control plane on the host level? Typically, we do that in form of a bridge. And I'm pretty sure that you have all used bridges in Linux networking before. But in this case, it's not a normal bridge. More precisely, it's a bridge that has certain additional features. For instance, what our bridge in this case can do is it can do package tagging. We will get to packet tagging on a later note in this presentation. But for now, remember that our control plane on our hosts actually has means of putting a stamp on every individual packet that comes in or goes out in order to assign that packet to our particular virtual machine. We will see why that is important on a later point in time. The overlay is the virtual space in which the complete networking happens. That's the room in which customer-created networks exist. This is the room where every customer is free to create as many virtual networks as he requires or as he thinks he requires. In fact, this is the case and this is the place where one customer can create 1,000 networks all with the same IP range if he considers that necessary. And this is everything the customer has to configure in the actual setup. How does the InterVM and InterHost communication work in software-defined networking? First, let's understand how assigning packets to individual virtual machines works. We have two hosts in the setup. Typically, what almost all cloud computing or SDN solutions do is they use VXLAN or GRE tunneling in the underlay. Remember that tunneling using VXLAN or GRE is not stateful. In fact, it's stateless. It's just a matter of assigning individual packets a certain level. That is a certain tag. That is the functionality I was referring to earlier. And by using these tags, or as they are typically called in the SDN context, IDs, I can actually determine what virtual machine a certain packet is coming from. And I can determine what hosts on a machine I am allowed to send an incoming packet to. And that's important because obviously VLAN on physical switches is used to separate customer traffic. And of course, I need the same functionality on my virtual networking infrastructure. So just because I cannot use switches anymore, it doesn't mean I do not need their features. I still need packet separation between customers. And if I have two virtual machines of two customers running on the same host, I still need those VMs traffic somehow to be separated. And this is where the VXLAN comes in. And this is where the ID assignment of VXLAN comes in very handy and very useful. Whenever a packet enters my host through the virtual switch, through my bridge, a certain ID is applied to that packet, and that packet ID assigns this packet to a certain customer. And only those VMs on the host running with the same ID in place will ever receive the packet. This is how traffic separation on the host level works. And this is also how communication between two individual hypervisor works. So if I have a virtual network, a virtual network on two hosts, and I do have that as soon as I have two virtual machines running on different hosts inside the cloud, everything that needs to happen is the packet coming out of my VM needs to be tagged by the SDN solution, in this case by the bridge that is responsible for doing VXLAN and GRE tunneling or GRE tunneling. Then it needs to be sent over the cable, and the host that receives the packet actually needs to read the ID that has been applied to that packet, and then transmit the actual packet to the VMs on the same host with the same ID. This is how traffic separation works. As you can see here, whenever you have a virtual, whenever you have software-defined networking in place, customer traffic is not going to get mixed. Because as soon as we have VXLAN or GRE tunneling or any comparable solution in place, we have packet ID assignments. And as soon as we have packet ID assignments, every actual packet is assigned to a virtual network, and virtual networks do not mix. I cannot reach one virtual network from within another, except for those cases in which I deliberately create a configuration that allows me to do that. And I need to do that using a router. So I need a virtual router to connect two virtual networks with each other. But by means of default configurations, I just cannot do that. I do not have a route to transmit packets from one server to another through the borders of virtual networks. And the same goes for internet connectivity. So in this case, it doesn't really matter a lot whether the host that my target system is running on is a virtual machine or something that connects me to the internet. Network gateways typically in the cloud context use another standard Linux kernel technology to allow network connectivity for virtual machines. These are called network namespaces, and in fact, network namespaces on internet gateways do exactly the same thing that the VXLAN or GRE tunneling does on individual hosts. What network namespaces on internet gateways in clouds really do is they separate customer traffic from each other. Again, if I have a network, or if I have two virtual machines of two different tenants on the same physical server, and they both need to talk to the internet, in clouds they will very often do it through one central gateway, or there may be one central gateway, or there may be more than one central gateway, but they are going to cross at some point. So there would be a danger of packet mix-up. And network namespaces in software-defined networking are typically used to avoid traffic mix-up of individual customer networks on the network gateways. So with this in mind, let's take a look at the SDN implementations we actually have available on the market right now. I think the description of the presentation mentions three. One is OpenVSwitch, the other is Contrail by Juniper, and the third is Midonet by Midokura. And I'm going to introduce these three individual solutions to you and mention the advantages, disadvantages, and also the most typical use cases for every one of them. Let's start with OpenVSwitch. OpenVSwitch, in fact, is based on OpenFlow. OpenFlow is an open standard on how to implement control planes in software. So what OpenFlow actually describes is if you need to implement a virtual control plane inside your installation, then these are typical standard functionalities that you will require. And if you implement them as we describe it, you will be able to use them inside a network on many individual hosts. OpenFlow is a standard that by now is available in a number of different revisions. The most widespread implementation of OpenFlow for Linux is OpenVSwitch. OpenVSwitch itself is a kernel technology, so there is a kernel module available on Linux machines named OpenVSwitch.ko. That OpenVSwitch module, in fact, is the part that on the bridge I have mentioned previously allows for the assignment of IDs to packets coming out of VMs. So whenever a packet comes out of VM, the bridge that this VM is connected to automatically assigns the ID to the packet, and that part is done by OpenVSwitch in the Linux kernel. The OpenVSwitch implementation in use on most Linux systems actually requires help. So the Linux kernel module does not assign packets automatically. Actually, what needs to happen is a configuration needs to put in place on the individual hosts and on the individual bridges. It needs to contain the information which ports are assigned which ID. OpenVSwitch only provides the technology to do that, but I need an agent or some other sort of external component to actually implement the assignment of IDs, or actually to configure it. The assignment is done by OpenVSwitch itself, I'm sorry, but the configuration on which port belongs to which ID needs to be done by an external agent. OpenVSwitch, as already mentioned earlier, uses VXLAN or GRE. Is anyone in the room not familiar with what GRE actually is? Okay, so GRE is generic routing encapsulation, and it really is just an encapsulation protocol for standard Ethernet links. It's an encapsulation protocol that does not do any encryption, actually. I think that's the best way to describe it. I've already mentioned the kernel module. The kernel module is used to create virtual switches on the individual hosts. And the one big problem that OpenVSwitch actually has is the fact that there is no central database of networking information, which leads to a lot of overhead. If you take a look at the OpenStack documentation that explains how to set up OpenVSwitch inside an OpenStack cloud, you will see a big fat hind explaining that the documentation contains a valid setup, but that this setup is only valid for a proof of concept installation. So let's take an example. Let's see what this actually means. I have a network of hypervisors, and I have many virtual machines running on these hypervisors inside my cloud. They are belonging to individual and different customers, so in fact, I need a way to talk from one VM to another. As you are probably all familiar with networking protocols, you know that before a virtual machine inside a setup like this can talk to another virtual machine, it needs to figure out where that virtual machine actually is. It needs to find out where it needs to send the packet in order to be able to reach the other virtual machine. And in OpenVSwitch, let's imagine we have this example. We want this virtual machine to talk to this virtual machine. What would happen now is ARP requests would be sent to all hosts inside the GRE network, creating a lot of overhead because, in fact, our virtual machine is not actually knowing where the other virtual machine is running. And the amount of overhead traffic produced inside an OpenVSwitch installation is massive compared to other solutions. I have seen setups in which the overhead of the OpenVSwitch installation has actually saturated the network. So the bigger the network grows, the more traffic you have, the more overhead traffic you have. This is not traffic caused by your customers. This is all traffic caused only by the overhead of your SDN solution. So whenever something goes wrong inside the setup, there's very little spare amount of capabilities left for any emergencies. This can easily saturate your network, and this is why all OpenVSwitch solutions, in fact, are marked as experimental or proof of concept. Whenever you try to install OpenStack or do anything that is related to OpenVSwitch, keep this in mind. If you want to run OpenVSwitch, in fact, OpenVSwitch is a wonderful technology, but as a standalone solution without any external hub, it actually is not going to be very useful for your setup. The second solution that we need to talk to is OpenContrail. OpenContrail is a solution that we at Sys11 have tested and evaluated very intense. We actually invested at least 1 year of time into looking into OpenContrail and trying to work with it. OpenContrail originally was designed by a company called Contrail. It was later bought by Juniper. And OpenContrail comes with a lot of very interesting and very great features when it comes to network connectivity. In terms of technology, in fact, OpenContrail probably is the most advanced solution on the market. There is a number of features inside OpenContrail that will wonderfully connect your virtual machines one to another. The setup of the thing actually is something that's hairy, but we'll come to that in a minute. If you take a look at the diagrams and the actual standards describing how virtualization in OpenContrail works, that is the one solution that will immediately give you the impression that these guys have actually gotten together their paperwork. OpenContrail, however, comes with a very, very big problem. Or actually, it comes with a number of different problems, and I will talk about these one after another. First of all, OpenContrail actually consists of at least 11 daemons, or it did the last time I looked into the thing. Probably by now it's going to be 13 to 15 if they continued to invent new daemons the speed they did when we were looking into it. And many of these will just crash. So many of these will basically just go away, and you will not even notice because they're immediately restarted by your init system or by Upstart or by whatever you have in place. And still, at some point, you will realize that functionality inside your cloud is not actually there because, again, this or that one component of OpenContrail has failed. So OpenContrail and a number of components that are part of OpenContrail, in fact, will not run in a reliable way. Also, there is a security problem. So one of the things the OpenContrail installer does is it downloads a very old version of bind, monkey patches it, and then installs this on your system so you can have DNS as a service. And it's going to be a 5 years old bind, and whenever somebody finds a flaw or a security hole in that bind, obviously you will be screwed because somebody will just make the bind crash, or in the worst case scenario, will just overtake the control over the bind installation that you would just have installed. So in fact, OpenFlow is not only unstable, it also is unreliable. During our tests and trials, we had a number of scenarios in which the software-defined networking layer did not actually behave as we would have expected, and it was not obvious for us why that was the case. We had a number of events in which the actual inventor of the software, so the guy that originally founded Contrail, was logging onto our service using Screen, and then disassembled parts of OpenContrail on the shell in GDB just to figure out what exactly might be the problem in this particular case. At 3 a.m. in the morning, which was very awesome, at least for him, because he's in the States, obviously. It's not something you want to have in production. It's like a black box, and whenever something is wrong with it, you will definitely require help from Contrail, and you will need somebody from Contrail to help you fix the thing. Another big problem that we have with OpenContrail is Technologydinger. What do I mean by that? Here is a list of technologies, scripting languages, and tools that are part of Contrail or need to be used for Contrail to work. OpenContrail comes with a separate kernel module that actually installs a separate networking driver in the Linux kernel. So traffic is caught in the Linux kernel by that kernel module. And whenever something goes wrong with the kernel module, if the machine actually boots up because the kernel module did not crash it this time, you will need to find somebody who is experienced in kernel programming to figure out why packets in the kernel are magically disappearing, which happened quite a few number of times during our evaluation. There is IFMAP. Who knows IFMAP? When we talked to the vendor, we were told that IFMAP is a standard that everybody knows these days. Very happy that's apparently not the case. We have Sandesh. Sandesh is the Indian word for a message. It was it is an invention by Contrail. So it's an invention, it's a protocol that was invented by the company that originally also invented Contrail. It's XML over Thrift. Who knows Thrift? Somebody at least. So they talk XML over Thrift, and that is what they use as their internal message bus. Except for those cases where they require a RabbitMQ because Thrift or Sandesh did not work for some reason. We have C++, Python, we have Node.js, we have IronD, which also is written in Java, we have Ruby, we have a number of shell scripts. For instance, the thing that I just mentioned about downloading and patching bind actually is a shell script. We have a number of databases and state configuration databases in use. We have Redis, we have Cassandra, we have Zookeeper, we have Kafka. In fact, the amount of traffic and billing data produced by Contrail was enough to saturate a free-node Cassandra cluster at ease, which was something that we also didn't like a lot. We have XMPP, we have BGP, we have MPLS. These are the great parts of OpenContrail because they try to use official protocols, because they try to use standards. Just the way they did it was not very smart in this case. We have the Enterprise edition of OpenContrail, which comes as a 700 megabytes large Debian package that will basically contain 600 Debian packages and unpack them to a temporary directory and then install them one after another using dpkg -i in the post installation script of the package. And that is what they will charge you for. So if you buy OpenContrail, or if you buy Contrail, because that is the commercial product, so it's Contrail and OpenContrail from Juniper, that is what you will basically get from them, and that is what they expect you to install. Of course, they have tested this probably on their Debian instance inside VirtualBox on their MacBook Air. I'm not sure about that, but that's basically what you get if you actually get the commercial version of it. So that is something you definitely don't want to have in your installation. It's a big black box. If it actually works, the OpenStack integration is great. So they have a separate module for the OpenStack networking service Neutron, and you can just load that module, and it's actually going to do what you expect it to do, at least most of the time. If all the other OpenContrail components work, of course, which many times they don't not. And you have open source software in its core. OpenContrail is available as open source software. There is commercial support available in a certain way. We were never able to actually find the one product inside Juniper, though, that would have given us this support. So we had contact to multiple people, and they weren't able to actually just sell us some sort of commercial support for this solution. You have a shiny web interface, though. So if things don't work, you can still click on the web interface and hope something gets better. Last but not least, there's Midonet. Midonet is completely different from OpenContrail. It's a development from scratch. The company itself is called Midokura. They are based in Japan, which is helpful sometimes if there is a problem inside the code. Because all you need to do is telling them that they put shame on the name of the company, and that gets things fixed really quickly. Midonet basically has OpenVSwitch at its core. The awesome thing is that they do not require any custom kernel module. They will just basically use whatever they find in the standard kernel of your distribution, and then they will apply their configuration on top of that kernel module that they find. It doesn't hurt to use a newer OpenVSwitch version than you can find in most of the Linux distributions available on the market. But in fact, it's not that necessary. So if you decide to go with your distribution kernel, you can just do that, and actually things are going to work pretty nifty. The one big difference between Midonet and the standard OpenVSwitch configuration is that Midonet adds the central database of knowledge that OpenVSwitch lacks. So if you remember the scenario that I had on the slides earlier, where one virtual machine tries to talk to another, and suddenly every virtual machine in the setup and every host gets a number of ARP requests because the things need to find each other first, this is solved in a very smart and way smarter way in Midonet than it actually is solved inside the basic OpenVSwitch setup. Let's imagine we have two virtual machines again, and they want to talk to each other. So the machine that is on the lower part of the slide needs to talk to the one that's on the upper part. And it needs to know how to reach it. It needs to know what physical host that virtual machine is on. It needs to know where to find the ARP address for that particular host. Typically, a switch would do that, having its ARP table available, but we do not have a physical switch in this case with the ARP table. So we need to replace that functionality. The virtual machine can actually ask the central database inside Midonet where to find that virtual machine. It only needs to do so once, because actually as soon as it knows where the virtual machine is, it can just put packages to that machine onto the so-called fast path. The answer in the machine in the database is actually stored. So the answer is this virtual machine can be found on that and that physical host. And now the virtual machine that needs to talk to the other one just knows where to find it and can actually start talking to the other virtual machine. And whenever these two need to talk again to each other, the whole process of figuring out where the other machine is not necessary anymore. In fact, this happens on the agent side of things. There is a separate agent for Midonet that's called Middleman. And Middleman actually emulates ARP answers. So whenever a virtual machine tries to find another one in the installation and it fires out ARP requests, this ARP request is never going to leave that particular machine. It will automatically be answered by the Middleman agent, and the virtual machine will still know where the other target virtual machine is. This reduces the overhead massively, and as already mentioned, it only requires the standard OpenVSwitch kernel module. Midonet is very well integrated with OpenStack. In fact, OpenStack is the #1 de facto showcase for Midonet. I think they support other virtualization solutions, but the only thing they ever actively advertise for is the OpenVSwitch part of things. And there is by now a small number of really big public clouds running Midonet. In fact, we also decided to go with the solution in the end, at least for now, based on the experiences that we have made with the other solutions. It's open source software, but commercial support is available. If you ask them that you want to buy support, they will sell it to you, which is awesome if you had been fiddling with Juniper for a month prior to that. And they also have a shiny web interface. So whatever you want to do inside Midonet can be done on the command line. It can be done using Puppet. They by now are working on Ansible integration, which is going to be awesome. And they also have a shiny web interface in which you can just click on things. That was a brief comparison of the three different technologies. Are there any questions from your side? Now is the time to ask them. I will not go until somebody asks. Yes, thanks. Just a minute.
Okay. What about failover functionality of this database, where the networking information is based on?
For Midonet, you mean?
Yeah.
Okay, so all configuration inside Midonet is in fact stored in Zookeeper. Zookeeper itself is a reliable database or a redundant database. You can have a Zookeeper cluster. And in contrast to other solutions, Zookeeper is able to take care of its clustering very well. So as soon as you have a Zookeeper instance failing, the only thing that will happen is other virtual machines, other middleman agents in the setup that previously talked to the one now failed Zookeeper instance will automatically talk to another one.
Okay.
Further
Any more questions, anyone?
First row.
What would happen if you have a failed hypervisor and the virtual machine moves to the next one?
So the question is, does a virtual machine migrate over to another hypervisor if the one that it's running on fails? From the SDN side of things in OpenStack, that's not a problem. Midonet can do that. Actually, it will automatically adapt its internal database to know that the virtual machine is now running on another host. Just like it would if you live migrate a machine, live migration is supported as well. The big problem in the OpenStack example is likely going to be OpenStack, because OpenStack by now is not able to migrate a virtual machine or to actually restart a virtual machine from a failed host on another host unless you explicitly tell it to do so. So it doesn't do that automatically, but that is more a problem of the cloud solution, not of the SDN solution. The SDN solution, Midonet in this case, actually supports that without any trouble. Did it answer the question? That's what I thought, yeah, seeing your face. The middleman agent running on the machine actually sends a typical ping to the actual Midonet API. So there's an API available in the setup, and every agent regularly reports to the API that it's still alive. Again, though, and that's important to understand here, migrating or restarting a failed VM on another host is something the cloud solution needs to initialize. So what Midonet really needs to do is just catch the notice that this virtual machine now is migrated to another host or is started on another host, and then act accordingly. That's not something that the SDN solution has a lot of stake in. Yes, please. They make sure you get some training.
Just to make sure, for Midonet, the agent only lives in the host and the VM itself sees a standard Ethernet interface.
That's right, yeah. In fact, what the middleman agent does is it does create a tap interface on the host that is then part of the virtual machine, but there is no component of Midonet whatsoever, of any SDN solution for that matter, running inside the virtual machine. For a virtual machine, when running on top of SDN, the networking looks exactly like it would look if it just was a standard virtualization host with KVN or XAN or something.
And the package handling in the host is completely done with the OpenVSwitch kernel module, and there's no other handling concerning the data in the packet itself.
Not for the SDN part of the solution. Anything that relates to the SDN solution is taken care of by the OpenVSwitch kernel module if the task needs to be done in the kernel, yes. So
Thanks.
the GRE tunneling and the VXLAN tunneling, for instance. Are there any further questions? Okay, so I have some final remarks. First of all, if you are able to speak German, there is an article on the whole thing I've been talking about on Golem. Actually, it was written by me, which is a nice coincidence. So if you want to read up on today's presentation, you can just go ahead and read this article. It's available for free on the internet. If you want a more distinct explanation of OpenContrail and what OpenContrail actually is, there's another article available, also written by me. This is behind a paywall, though. So if you have this issue of the German EX newspaper, then you can still read it. On the other, if you don't have that, you can actually buy the PDF on the link. And the same goes for Midonet. Actually, I just had this in the post yesterday, so there's an article in this issue of the newspaper on Midonet written by me as well. And if you want to look at it, then just go ahead. And the most important thing actually is, if you like cake, we are hiring. So this is the amount of cake that we had served in the last 4 months at SIS11 by individual employees. And if you like cake, then please feel free to just give us a call or go to the website and have a look. And we'll be very happy to have you and have you bring cake or have you eat cake, whatever you prefer more. Thank you.